Welcome to Physics 2211, Lab 1. Before we start, let's make some assumptions. There's no air resistance, there's no friction, and the experiment is done on a flat surface. The system is a can of mass 0.425 kilograms. The surroundings include everything else in the environment, like the curtains, the ruler, the extension cord, etc. The center of the can is at 0.04795 meters in the positive x direction. The initial velocity of the can is 0.465 meters per second, also in the positive x direction. The purpose of this lab is to observe the motion of an object moving at the same speed without changing direction, also constant velocity, and we will use a computational model to compare with the tracker results to observe and verify Newton's second law. Newton's first law and Newton's second law are the fundamental physics principles that we need. Newton's first law states that an object in motion or rest will stay in the same motion or at rest until acted upon by an outside force. And Newton's second law states that the net force acting on an object is equal to the change in momentum over the change in time. The velocity update formula shows that the final velocity is equal to the initial velocity plus the net force divided by mass times delta t, and the position update formula shows that the final position is equal to the initial position plus the average velocity times delta t, and the momentum update formula shows that the final momentum is equal to the initial momentum plus the net force times delta t. Now, per Newton's first law, the velocity update formula and the momentum update formula need to have a net force of 0. We need this in the velocity update formula because without a 0 net force, we won't have a constant velocity, so we need a 0 net force. And equivalently, this means in the momentum update formula, the momentum is also constant throughout this lab. The observations almost match the computer expected model with a few slight differences, which is most likely due to the uncontrolled environment, but we'll talk about this more when we get to the results again. And here's an image of the experiment, and here's our code. On the right, we have our initial conditions as stated before, along with delta t, and on the left we have again the 0 net force and the updates and the update formulas for velocity and position. And now we have our models in the form of position versus time charts, and on the left the glow script model shows that the position should go in the positive x direction in a straight line as time goes forward, but as we can see, that's not exactly the case in the data we found. And as stated earlier, the constant velocity is the reason why we have a straight line going in the positive x direction as time goes forward, and the differences may be due to the uncontrolled environment. Many objects were in the surroundings, and a lot of them exerted forces on our system, which is the can, and that may have caused the differences that we see in the chart. The human error or video error may also have a role in this, because certain frames were a little blurry and it was a little hard to find the center of the can, so human or video error may also be sources of error for the differences. Now, let's address some questions. What if we were to flip the axes? Then we would observe velocity with the same magnitude, but the direction would just be flipped. In this case, it would be in the, as time goes forward, position would go down in the negative x direction, but besides that, nothing else would change because velocity is constant. And is it possible to say how many pushes or pulls were being added together to give the zero net force? It's not possible to say how many pushes or pulls were being added together because there were numerous things in the surroundings that could have acted on our system. Thank you for watching and have a good day.